We're going to talk about solving systems of equations by graphing, substitution, and elimination. I try to keep these videos rather short. This one's going to be kind of on the long side because it's basically 3 lessons snapped into one. So if all you're here for is how to solve by substitution, if you don't care about graphing or elimination, you can scroll down on your YouTube, scroll down to the info, and jump to each of these 3 sections. We're going to cover solving by graphing, either by hand or calculator with Desmos, the app, solving by substitution, solving by elimination, which is also known as the addition or combination methods, solving with fractions and decimals, and one thing that I didn't list was having no solutions or infinite solutions. That'll be at the end. Any of those things you can jump to down below. I have timestamps, but let's start talking about solving with graphing. You want to solve with graphing whenever you have a graphing calculator or a graphing app like Desmos. If you want to be able to see multiple possibilities at once, or maybe just if the equations come to you in a form that graphs really well. But usually if something graphs really well, it'll also substitute or eliminate really well. So usually graphing isn't the most efficient method, but sometimes it's got its value, especially if you're doing one of these things up here. So I'm going to graph these 2 equations. This first one is in slope-intercept form, slope y-intercept. And I'll give you a quick graphing review. This is called our slope. It's m. And we'll actually think of it as 3 over 1. We're going to go up 3, right 1. If this were a negative slope, pretend it was like negative 2 over 3, we would go down to right 3. So I always have the negative mean up or down, and then this number on the bottom always means go to the right. We call slope rise over run. This is Algebra 1 review, so I'm going to move on past it. So our slope is 3, that's up 3, right 1. This is our y-intercept. We call it the b value. The y-intercept is negative 4, so we're going to cross the y-axis of our graph at negative 4. And before I actually build the graph and the plane and all the coordinates and stuff, I'm going to look at both of my equations and see how they're going to graph. This is in standard form. Standard form is called ax plus by equals c. That's what I have written over here. So in this case, the a value is negative 5, the b value is 2, and the c value is negative 10. There's a few ways to solve from standard form, or to graph, from standard form. I'll show you 2 of them. One of them is to find the intercepts. So the x-intercept, where the graph crosses the x-axis, is always at c over a, which in this case is negative 10 over negative 5, which is 2. It's the point 2, 0. The y-intercept, where the graph crosses the y-axis, is at c over b, which is negative 10 over 2, which is negative 5. That's the point 0, negative 5. If we're crossing the y-axis, the x value must be 0. And a lot of people don't talk about this one, but you can actually find the slope. We use letter m for slope. You can find the slope by doing negative a over b, which is negative 5 or positive 5 over 2. So the slope of this is going to be 5 over 2. So now I know that my yellow line is starting at negative 4. My green line is starting at negative 5. So when I build my axes, I don't actually want them to be like smack in the middle. I'm going to think about the fact that I know, this will be my y-axis, so I'll just make it nice and long. I know that I'm starting kind of below the x-axis, so I'm going to give myself more space on the bottom than I am on top. One thing I do is I pretty rarely use pre-constructed grids and axes and coordinate planes, so that I can give myself space to put things where I want them. So for my yellow equation, y equals 3x minus 4, I start at negative 4, which is here. I'm going to label that negative 4. My graph is going up 3, right 1, up 3, right 1, and put down as many dots as you possibly can. So here's down 3, left 1, down 3, left 1, down 3, left 1. If I'm going up and right, it's the same as going down and left. This line has a positive slope. It's going to graph like this. Ooh, I don't know what just happened, so I'm going to undo that. I think I got off my line tool. I wanted a yellow line. Let's see, is this still going to do that thing? Yeah. Shoot, excuse me. Let's just try this again. There we go. Nice, pretty yellow line. Now I'll do the green one. The green one has a y-intercept at negative 5, which would be here, an x-intercept at 2, which would be here, and a slope of 5 over 2. So I can keep going up 5 and right 2, Or I can start going down 5 and left 2. Ah, they're crossing right here. I'll just keep on putting down a few points to show you how close these can look. The reason I say that putting down so many dots is so important is when I graph this green line, even though I'm using a machine and I'm making perfectly straight lines and everything, like I could not do this more accurately by hand, it still kind of looks like they're crossing right here. Because I'm still doing it by hand, it's still not perfect. So I don't want to trust my eyes, I want to trust the data. I saw the two dots crossed each other right there. That is the actual point of intersection. And that is negative 4, 5, 6, 7, 8, 9, 10, negative 2. So it's the point negative 2, negative 10. That is the actual point of intersection of these two lines, even though it looks like it might be in here somewhere. That's why you put down a lot of dots in both directions, because you need the two dots to fall on top of each other. If they don't fall on top of each other, then they're not crossing at a whole number point. And that's okay. It just means the graph can't give you the precise whole number point if you do it by hand. Now we're going to check this. And oh my goodness, you should always check these. There's no point in doing all this work if you can't actually be sure you got it right or wrong. You don't want to be doing the wrong thing over and over. I'm going to plug negative 2 in for x and negative 10 in for y. So the first one I get negative 10 equals 3 times negative 2 minus 4, and I'm checking to see if these are equal. So I put that question up there. It's like, are these equal? I don't know. Let's check. Negative 10 does equal negative 10. That one checks. So now I'll plug in negative 2 for this x, and I will plug in negative 5 for the negative 10 for this x, and I get, I'll do this work down here, negative 5 times negative 2 plus 2 times negative 10, and I really hope this is equal to negative 10, and 10 minus 20 does equal negative 10, so it checks. So this is the point of intersection. What that point is, what you're looking for when you're solving, you're trying to find the one point that works in both equations. This is the one point that works in both equations. It was this point here. And that's what I'm trying to find. That's the solution to the system. Another way to do this is on your graphing calculator. Here's a TI-83. Oh, I'm sorry. Before I do this, let me talk about, I said that there were two ways to graph this equation. Let me show those two ways and first clean this up a little bit. So let me get rid of all this. Remember, you can always pause if you want to pause or rewind to go back and see things. There's another way to graph this. Is this red too dark? Probably. I'm going to stop talking to myself soon, I promise. I'm going to take negative 5x plus 2y equals negative 10. I could find the x and y intercepts in the slope, but I could also just put it in slope-intercept form, meaning I can get the y by itself. So I shouldn't have written that plus 2y. It's just 2y equals 5x minus 10. I'll divide everything by 2. When you divide by 2, make things fractions and make them improper fractions, not mixed numbers. Don't make this 2.5 or 2.5. Keep it 5 over 2x minus 5. Now I have a y-intercept, and now I have a slope. This would start at negative 5, which is here, and go up 5, right 2, which is here, and it would hit all these same points. This follows the same graph. So you can always take any equation you're given and put it into slope-intercept form. It's not always the most efficient way, and a lot of you will rely on that too much, but it can be done that way. Here's my graphing calculator. The graphing calculator, I'm going to do this quickly, but you press the y equals, which is the top left button. And the y equals means you literally have the letter y over here. So it's like this y is this y here. So I'm going to write y equals 3x minus 4. And this button next to alpha is the x. So here's x over and over and over. I'm going to delete all these. I don't want all of them, but there's your variable button x. The next one still has to have the y equals, so I need to use this equation here because the y is by itself there. 5 divided by 2, x minus 5. Now I'll press enter, I'll graph, and it looks like that. And just like my graph over here, it's kind of tough to tell where they're crossing. So one thing I'm going to do is zoom out a little bit. Right now my x values are going from negative 10 to 10. Let's make it negative 15 to 15. And the y's are going to go from negative 15 to 15 also. So I just press the window button to change my window, meaning the screen I'm looking at. Now when I see the graph, it's definitely happening somewhere in here because I have this little spot where they start to break apart, like down here is that little spot where they start to break apart. I want to find the precise point of intersection, so I press second Trace. Trace is a top right button next to graph. And this brings up my calc or calculate menu, which has a lot of useful things, one of which is intersect. So I'm going to go to intersect and I'm going to press enter, and it's going to ask me for the first curve. All that means is which line do I want to be on. If you only have 2 lines of graphs, it doesn't matter. But if you want to switch because you have more than 2 lines, you can press up and down and jump between lines. Since I only have 2 lines, it doesn't matter. Just press enter. Second curve, press enter again because you're on the next line. It says guess, ignore that entirely. Press enter one more time. It intersects at -2, -10, just like we found. So there's solving by graphing on your calculator. Really, really useful. This second trace pulls up lots of useful options. These first 5 in particular can do a lot of good things for you. Desmos is, I think, in a lot of ways superior to a calculator. In a perfect world, we could use it all the time, but we're not quite in that perfect world yet. Maybe you are by the time you're watching this video. I'm just going to type in for the first equation, y equals 3x minus 4. And it starts graphing as I go. You'll notice here, there's a vertical line. Here, it snuck in the x. Now it sneaks in the y-intercept. It just types as you go. The nice thing about Desmos is I don't have to solve. I can just write down the equation. I don't have to get the y by itself, just type in the equation. Now when I look at this is a -10, I think. Yeah, -10. They're crossing here. And to find out where that is, you just tap the lines, and it'll pull up where they cross. Just tap it, and it shows you at -2, -10 is your solution. There's Desmos. I'll let you play with both, either Desmos or calculator, as much as you want, because they're useful things. And now we will move on to substitution. Okay, now we're going to solve by substitution. Substitution is a method where you get one variable by itself and plug it into the other equation. You want to use this method whenever you can easily isolate a variable. And what that means is you can get a variable by itself without having fractions or decimals. So here's what you want to do. You want to look at each variable and see if I got it by itself, would I make any fractions? By which I mean, like, to get this a by itself, I would at some point in the process divide everything by 3. And that gets me a fraction here, and I don't want that. So I'm not going to get that a by itself. If I get this b by itself, I would at some point in the process divide everything by -4. And that gets me 2 fractions, and I don't want either of those. That's no good. If I were to divide everything by that 6 in front of the a, I get a fraction here, and don't want that. And here, if I were to divide everything by this -2, whole number, whole number, whole number. That's what I want. So this -2b, that is the variable, or that b, really, the b is what I want to get by itself. So I'm going to rewrite the equation over here to give myself some room and get that b by itself. So subtract 6a from both sides, divide both sides by -2, and now I know that b equals 3a minus 6. So I can take this b, which is 3a minus 6, and plug it into the other equation's b. It has to be the other equation, it can't be the same one. So I have now 3a minus 4b, but the b becomes 3a minus 6, and that equals -3. This b got replaced by this b, because b is 3a minus 6. Now I'll distribute the -4, so 3a minus 12a plus 24 equals -3. And you see what happened? I now only have one variable. I used to have 2. I used to have a and b. Now I just have one a, which means I can solve, and that's the sneaky little trick of substitution. You get down to just one variable. So -9a equals -27, so a is going to equal 3. If a equals 3, and here's one of the nice things about the substitution method that I use, I put this in a box up here for 2 reasons. One is so I knew what I was plugging in for this b here, but also this can just go in the box now. If I plug a in for that 3, I can find b. So b is going to equal 3 times 3 minus 6, which is 9 minus 6, which is also 3. This is the 0.33. A is 3, b is 3. Try and give your points in alphabetical order, or in terms of inputs and outputs, or independent variable first. But alphabetical order if you don't know otherwise. I'm going to check. You should always check. Checking is crucial. I'm going to plug in a 3 for the A's and a 3 for the B's, and I'll just do that real quick. 18 minus 6 equals 12. 9 minus 12 equals -3. It checks. There's my solution. It's the 0.33. That's the one point that works in both equations. There's substitution for you. If you can get a variable by itself without a fraction or a decimal, it's very convenient. However, that's not always a very good option. One thing about substitution I want to discuss, and that's actually the importance of the equal sign. Usually when I teach a class, the first thing I talk about is, what does the equal sign mean? And it's funny because, I just wrote the equal sign over here a dozen times at least. And you've probably written it 1,000 times, 100,000 times in your life as you've done math. Arithmetic, really. And you might think of it as like, well, okay, we know that 2 plus 3 equals 5. You probably think of the left side as the problem and the right side as the answer. And the equal sign is the magic thing that splits up the problem from the answer. And I think this comes from grade school, when you would just do worksheet after worksheet after worksheet of arithmetic. And always be like 6 plus something equals blank. So you would view the left side as the problem. The problem is 3 plus 1. And the right side is the answer. 3 plus 1 is 4, 2 minus 1 is 1, 5 plus 0 is 5, and 6 plus 0 is 60. And I'm joking, I know it's 6. But that's not really what the equal sign is trying to tell us. It's actually not problem and answer. And you might know this, but let's just make this really, really clear. The equal sign means is or same. It means one side is the same as the other. So if I have 3, that's the same as 3, but it's also the same as 2 plus 1, and 2 plus 1 is also the same as 3. One side is the same as the other. And the fact that we can say that is actually kind of rare. That's one of the special things about math, and one of the things that I really like about it. We can actually say one thing equals the other. And in society today, equality is such a tough thing to deal with. How can you say that 2 groups or 2 jobs or 2 pays or 2 anything are the same when there's so many complexities to everything? But in math, what we can say is that the value of something on the left is the same as the value of something on the right. Usually it's like the actual number, like the number here matches the number here. And we can say it's the same. And that's wonderful. That makes things very convenient, because over here I can say B is 3a minus 6. B is the same as 3a minus 6, which is why I can take this B and replace it with that 3a minus 6, because this is actually the same as this. They're actually equal to each other, so the result that I get here I can trust from where I started, because one thing was the same as the next, all these things were the same as each other. Even with graphing, we can say y is some value, plug that number in for the value. So say I plug in a 2 for x. Well, if x is 2, y is 2. When x is 2, y is 2, that would be the point 2, 2, which was here, 2, 2. The equal sign meaning same is a very important idea that I refer to a lot. But let's move on to elimination, which is also known as combination or addition, but I'm going to call it the elimination method moving forward. Let's pick a new color. My goal when I'm eliminating is to add up 2 equations so that one of the variables cancels. And the way that I just phrase that, add up 2 equations, is actually not really precise, but just, we're going to live with it. I want to get these to look like each other. Right now, this y is on the right side of the equal sign, but this y is on the left. So I'm going to subtract 3y from both sides. So I get 3x minus 8y equals 4, and 2x minus 3y equals 5. I want to make it so that 2 coefficients on the same variable have the same value, but opposite signs. By which I mean, if I could possibly get like a negative 8y on top and a negative 8y on the bottom, positive 8y on the bottom, that would be good. If I can get 2 coefficients to be the same, I'm going to try and do that. And what I use is one of my tools of algebra. Over here I've listed the 4 tools of algebra. And this isn't everything we do in algebra, but they're the 4 most common things, the 4 ways to manipulate equations or expressions. You can add 0, multiply by 1, do the same thing to both sides of an equation, or substitute equivalent values. We did this in substitution. I'm going to do this here. I can multiply either side of the equation by whatever I want. So if I multiply the top equation by 2 and the bottom equation by 3 on both sides, I'm going to get 6x minus 16y equals 8 and 6x minus 9y equals 15. And what I've done is I've made these two variables match, 6x and 6x. I actually don't want them to be perfect matches. I want them to be opposites of each other. So I'm going to switch this to a negative 3. When I make that a negative 3, all of these signs just switch. Negative 6x, positive 9y, negative 15. Now these two variables have the same coefficient with different signs. Remember, coefficient means the number in front of the variable. And if I were to add these up, which I'm going to do, the x values cancel, and I'm going to get negative 7y equals negative 7. The x's are gone. I'm down to just one variable y, which is always the goal when solving it down to one variable. Divide both sides by negative 7, and I get y equals 1. Now that I know that y equals 1, I actually have two options, and one of them is just to plug this back into either equation. So I'm going to plug this in up here to this equation for y. I'm going to get 2x minus 3 times 1 equals 5. Well, this means that 2x minus 3 equals 5, so 2x equals 8, and x equals 4. My solution would be the point 41. I'm going to check that real quick. I'll check that in my original equation. You should always check in the original in case you made a mistake somewhere in the process. So I'm going to plug a 4 in for x and a 1 in for y. 12 minus 8 equals 4. Plug a 4 in for x and a 1 in for y. 8 equals 3 plus 5. That checks. So this is my solution. Good. So now here's what the main question becomes. The main issue is, where on earth did I get those two numbers from? How can I find those two numbers specifically? That becomes the challenge, but it's actually a very, very simple process. So I'm going to clear the screen right now, meaning if you want to look at this, you can go pause and go back and look at it. But I'm going to clear the screen and show you a way that you can always do this. Suppose that I just had letters. ax plus by equals c, and dx plus ey equals f. There's a whole bunch of letters here. But let a, b, c, d, e, and f represent coefficients, and x and y are still the variables x and y. So it's like here, this would be a, this would be b, this would be c. This wouldn't quite be d because it's in the wrong spot of the equation, but I hope you get the idea. What you can always do, this will always work, is take this variable, this coefficient here, and multiply it here. I can do the left or the bottom equation by a on the top and bottom. And I can do the bottom equation. I can take this variable and put it here, multiply it by d on top and bottom. And that's going to give me a dx plus b dy equals cd, and a dx plus a ey equals af. And I would like one of these to be negative, so I'll switch this sign and switch this sign, which makes this negative, 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 so that when I add these are going to cancel. You can always just take the coefficient from one of them and attach it to the other, and vice versa. So I'll show that now with the first example that I had. Remember, the first example, I had to move a term over originally. So I wrote this as 3x minus 8y equals 4, and 2x minus 3y equals 5. Well, this is exactly what I did. I took this 3 and multiplied it here, and I took the 2, and I'll pick a different color here. I took this 2 and multiplied it here. Then I realized one of these had to be negative, so I made the bottom one negative, because why not? And that's how I got my result. That method can always, always work. You just might have to make something a negative every once in a while, but not always. So that's how you can find your coefficients to multiply by. And now, I'm going to take a bit of a break from solving this and ask a really important question. Why? Why does this method work? Where does this come from? And this is something that you probably haven't thought to ask because you've never really cared, quite frankly. Or maybe when you were young you used to ask these questions and you don't anymore. But why? You know, like, why does this happen? Oh boy. I shouldn't have sided like that. I'm going to have to delete that in editing. So now I want to discuss why this works. In fact, I think the question of why is one of the most important and useful and informative questions we can ask. And my guess is that you've been conditioned at this point in your math career to rarely question why things happen the way they happen. Like, you know, you don't question why a negative times a negative is a positive, or why subtracting two negatives becomes adding the positive, things like that, because you've just been trained to accept it as the answer. Well, I want to answer the question of why the elimination method works. So in this case, we could just add these up as they are, because these y's are already canceling, and get 8x equals 8, which means that x would equal 1. But why can we do that, is my question. I'm going to move this over and we'll talk about that. Back to the 4 tools of algebra, I can do the same thing to both sides of an equation whenever I want. So if I wanted to, I could add 10 to both sides. And that seems silly. Why would you do that? 5x minus 2y plus 10 equals 11. That's not helpful at all. But the fact of the matter is I could do it if I wanted to. In fact, if I wanted to, I could multiply both sides by 8. I could divide both sides by 2/3. Or I could take both sides to the 3rd power if I actually wanted to, and I really don't. But as long as I'm doing the same thing to both sides of an equation, I can do whatever I want. Well, one thing I could do, and this is actually going to be kind of helpful, is I could add 7 to both sides. And right now you look at that, and that doesn't look very helpful, because I get 5x minus 2y plus 7 equals 8. But I know that 7 is 3x plus 2y. So instead of adding 7 to both sides, I add 7 to both sides. That 7 is supposed to be a y. This is just 7. So I'm adding the same thing to both sides of the equation. I'm following my step 3, and that gets me 8x equals 8, which in this case means that x equals 1. Now I can go back and find y. Y is going to be 2. The reason this works is because I'm adding the same thing to both sides of the equation. I'm not actually adding equations up together. We describe it that way because that's the most simple way to describe it, but that's not actually what's happening. I'm adding expressions. Here's an expression, I add those up. Here's an expression, I add those up. So I can solve it that way. And this also kind of leads me to another sort of helpful way to solve these, especially once we start talking about matrices in a couple of chapters. I just talked about how I could add up these two equations and get 8x equals 8, so x equals 1. And one way to solve this would be to take this 1 and plug it back into one of these x's here. But another way to solve this, and sometimes this can be really convenient, instead of canceling the y's out, I'm going to cancel the x's out. Multiply the top equation by 3, and multiply the bottom equation by -5. That gets me 15x minus 6y equals 3, negative 15x minus 10y equals negative 35. I add these up, I'll get negative 16y equals negative 38. Nope, negative 32, excuse me. So y equals 2. My solution, I already had x equals 1. Now I found y equals 2. My solution is the 0.12. So instead of going back and resubstituting, I could just eliminate the other variable. You can do elimination twice, or you can just go back and resubstitute. This was the substitution method where I took it and I plugged it back in. This is me just eliminating twice. Either one is fine. They both have their uses, whichever you prefer. Okay, let's talk about fractions and decimals, and I call this just get over it, because you have to deal with them. If you've been living in a world where there weren't fractions or decimals or negatives when you got your final results, that's going to change. I want to kill these fractions. I'm like you, I don't like fractions. So I'm going to kill them whenever I can. That's actually a lie, I kind of love them, but let's pretend like I'm like you. This is also a fraction 3 over 1. And the numbers 2, 3, and 1 have a least common multiple, or in this case a lowest common denominator, I'll just call it a denominator, of 6. So I can get everything to have a denominator of 6. I can take this and multiply the top and the bottom by 3 over 3, multiply the top and the bottom by 2 over 2, and the top and the bottom by 6 over 6. You'll notice what I was doing there was multiplying by 1. I was doing this thing right here. I can do that whenever I want. I multiplied by 1 a bunch of places. And that gets me 3x over 6 plus 4y over 6 equals 18 over 6. And now I can just drop the denominators. Get a common denominator, drop the denominators. The way I'm doing that, the step I'm not showing, which you can actually do, is I'm just multiplying everything by 6. And that cancels, 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 cancels to get me this. There, I've killed off these fractions. Here, I'm going to kill off the decimals. I'm going to multiply everything by 100 because I have to move this decimal twice. And that gets me 30x minus 5y equals 20. Then I would solve this system. You can solve it by substitution, elimination, or graphing. I don't really care. I don't think I'm going to show that. What the heck, I might as well. I'll do that real quick. If you want to skip it or fast forward or whatever, you can, but I'm going to go for this. Because it's kind of simple. I'm going to multiply the top equation by negative 10. That gets me this, which I can then add up with this, and I get Is this going to come out clean? Probably not. I just made it up. So y is going to equal 160 over 45 because the negative cancels. Divide everything by 5. I can get 9 over 20, 30, 40, 50, 60, 70, 80. What's 160 divided by 5? Oh, I'm embarrassing myself. 32. 32 over 9. I would then plug that back in up here, or eliminate the y's. This is where showing that other method's kind of nice. I could also do 3x plus 4y equals 18. 30x minus 5y equals 20. I'll multiply the top equation by 5 and the bottom equation by 4. This is going to cancel the y's out. So I get 15x plus 20y equals 90, and 120x minus 20y equals 80. I add these up and I get 135x equals 170. So x equals 170 over 135, which I could also reduce 34 over 27. If I divide the top and the bottom by 5, yeah, that was way less embarrassing that time. There, clear fractions, clear decimals, deal with it. Finally, we'll talk about the situations of no solutions, infinite solutions, and 0 as a solution. No solutions means you have parallel lines. So these two lines right now have the same slope, 5. But they have different y-intercepts. This has a y-intercept of -1. This has a y-intercept of 0. There's a plus 0 you can snack onto the end there if you'd like. Since they have the same slope but different y-intercepts, they're parallel lines, they will have no solutions. And I can show that in this way using substitution. This y equals 5x minus 1. I can take this and plug it in for the other y. That gives me 5x minus 1 equals 5x. Now when I solve this, I want to get the x's on the same side of the equation first. So I'm going to subtract 5x from both sides. That gives me -1 equals 0. And that is when you can see that this has no solutions. This has no variables, and it's a lie, by which I mean -1 does not actually equal 0. This has no solutions. Whenever you get something like 1 equals 0, 6 equals 5, -3 equals 2, some untrue statement without variables, that is no solutions. Now this one over here is going to be infinite solutions. It's going to be the same line twice. If we were to graph this, it'd give us the same line just graphed on top of itself. So I'm going to multiply the top equation by 3, and the bottom equation by 2. Using that trick I showed before, I just took these coefficients and multiplied them in the other equation. So that's 6x minus 18y equals 12, and negative 6x plus 18y equals negative 12. And when I add all these up, I get 0 equals 0. That's the truth. If you get 0 equals 0, or 3 equals 3, or 10 equals 10, some true statement without variables, then you have infinite solutions. Please understand, infinite solutions doesn't mean everything will work. It just means that there's a whole bunch of things that work. There's an infinite collection of things that work. So like if I took the original equation, 2x minus 6y equals 4, and I'm going to get the x by itself, I'll get the y by itself to be consistent. Divide everything by negative 6, and I get y equals 1/3 x minus 2/3. Any point that works in this equation will also work in this equation. That doesn't mean every point works, but there's still an infinite number of points that work. Any solutions that come in this form are going to work. Now the third thing that I want to show is 0 as a solution, because this often confuses people. This is not going to be no solutions, not going to be infinite solutions. I'm just going to add up these two equations, because right now the y's are going to cancel, and I get 2x equals 0. This still has a variable in it. Notice how here there was no variable, so we said no solutions. Here there was no variable, we said infinite solutions. This still has a variable in it. Divide both sides by 2. 0 divided by 2 is 0. X equals 0 is part of the solution. X equals 0, so I plug that back in here. If x equals 0, then I know that 2y must equal 10, so y equals 5. The solution is the point 0, 5. If you check it in both equations, it works. So x equals 0 is not the same as no solutions, it just means 0 is part of the solution. Please don't get confused by those. Thank you for watching. If you have any questions, you can leave them in the comments below, and I'll try and respond to them. Have a great day. Hey, thanks for watching. I hope that was helpful. If you have any questions, leave them in the comments down below. There can be questions about the video you saw here or anything else in math I'm happy to help with. Subscribe if you'd like to watch more videos or see other updates as they come. I'm going to try to run through all of Algebra 2 Trig and then eventually hit more classes like Algebra 1 and Geometry and Pre-Calc and everything else. If you have questions about stuff covered that's not in this video, still let me know. I'm happy to help. And finally, if you're not one of my students taking the class, but you found the video and are watching it, or maybe you're a teacher and are watching it, you can buy the curriculum and buy the worksheets to go through it. That's found at the website listed down below also. So again, thanks for watching. Have a wonderful day.